Hey, my name is Elishai Ezra Tsur, and I am heading the Neuro-Biomorphic Engineering Lab at the Open University of Israel. This project was led by Hadar Cohen-Duwek, the lab manager, and supported by Yahia Showgan, a graduate student in computer science in the lab. Retinal visual inputs reflect the intricate anatomical and physiological characteristics of the retina, where visual cues are captured by non-evenly distributed photoreceptors across the retinopathic field. Retinal input is compressed and encoded by retinal ganglion cells that transmits only color changes. Moreover, the cell's receptive field's size varies, whereas its size becomes larger as the distance from the fovea increases. Therefore, in comparison to its periphery, the fovea features high visual resolution. Retinal color processing is also considered to deteriorate in the peripheral retina, where the visual signals are of low resolution and color cues. Another important characteristic of human vision is being based on saccade vision, where the eyes are constantly and successively fixating on changing locations several times per second. While human visual perception is stable, in saccade vision, retinal objects' projections are continuously altered, supposedly resulting in motion blur and instability. However, even though visual information is lacking in the peripheral retina, our subjective visual experience is that of sharp and colorful surfaces, both in the center and in the peripheral vision. Therefore, there is an apparent disparity between visual perception, which is colorful, complete, and in high resolution, and the saccadic and spatially heterogeneous retinal input data. In this work, we computationally emulated retinal inputs and used the neural network and adversarial optimization to demonstrate how retinal inputs can be used for the reconstruction of colorful images in high resolution. Our model may set the groundwork for the development of biologically plausible neural networks for computational vision perception.
To emulate retinal inputs, we acquired RGB and event data from the Neuro-Biomorphic dataset and Caltech. We used these images to computationally emulate foveated colors map and intensity channels, as well as intrasaccadic motion data. To emulate the ganglion cell's color opponent receptive field, input RGB images were converted to 3 opponent channels: 2 chromatic channels and 1 achromatic channel. To simulate the deficient color perception in the peripheral vision, we used a circular mask whose center was located at the chromatic channels. To simulate the intrasaccadic motion, we used a recording taken by a neuromorphic event camera, available through the Caltech dataset. Event-based cameras are considered as following the principles of biological sensing, only capturing changes in scene reflectance. They report only changes in brightness. Event cameras transmit asynchronous events representing changes in relative intensity at the pixel level with a high millisecond range temporal resolution. 3 saccade modalities were generated by virtually moving each image in front of an event camera. We utilized an artificial neural network for the reconstruction and colorization of the retinal inputs. We used a convolutional neural network with chromatic and achromatic pathways. In the achromatic pathway, high-frequency temporal and spatial information was used to reconstruct high-resolution intensity images, representing intrasaccadic motion and spatial edges. The chromatic pathway enhanced the peripheral vision's perception of color using UNet for image colorization. Our neural network comprises the following phases. First, a simple 5 layers convolutional neural network that predict Laplacian from the event frames as well as the foveated intensity Laplacian. Second, a Poisson solver layer that reconstructs the image from the predicted Laplacian input. And third, a unit model for image colorization. We further used a discriminator to train the network with adversarial examples. Our objective was to minimize the sum of the lost functions of each phase of the generator while maximizing the ability of the discriminator to detect fake and real examples. Our proposed model allows the reconstruction of a full, colorful, and high-resolution image from incomplete retinal information. An adversarially trained discriminator was trained to reconstruct realistic, colorful outputs.
Here you can see the original ground truth images and the reconstructed images with and without discriminator optimization. Our results demonstrate that our proposed network is capable of reconstructing high-quality images from retinal input which is lacking peripheral information with both training methods. To investigate the effect of intrasaccadic motion on the reconstructed images, we further trained our model with foveated images, RGB data without events. While the results without the discriminator optimization achieve better perceptual score in both SSIM and LPIPS, with the discriminator, the obtained images are more colorful in their peripheral areas. The reason for this may be that many images in the dataset have large greenish areas in their background. Without event data representing intrasaccadic motion, the reconstructed images are not as sharp in the periphery as they are with event data. The blurring effect is particularly noticeable in images with high detail texture. Interestingly, when the discriminator optimization is used without events, the colors appear to be corrupted.
We would like to thank our funders and partners, and we are looking forward to seeing you all in the conference.